The calculus controversy was an argument between 17th-century mathematicians Isaac Newton and Gottfried Leibniz over who had first invented the mathematical study of change. Calculus. It is a question that had been the cause of a major intellectual controversy. One act began simmering in 1699 and broke out in full force in 1711. Newton claimed to have begun working on a form of the calculus in 1666, at the age of 23, but did not publish it except as a minor annotation in the back of one of his publications decades later. Gottfried Leibniz began working on his variant of the calculus in 1674, and in 1684 published his first paper employing it. L'Hôpital published a text on Leibniz's calculus in 1696. Meanwhile, Newton, though he explained his form of calculus in Section I of Book 1 of the Principia of 1687, did not explain his eventual fluxional notation for the calculus in print until 1693 and 1704. Background. The last years of Leibniz's life, 1710 to 1716, were embittered by a long controversy with John Keill, Newton, and others, over whether Leibniz had discovered calculus independently of Newton, or whether he had merely invented another notation for ideas that were fundamentally Newton's. Newton manipulated the quarrel. The most remarkable aspect of this struggle was that no participant doubted for a moment that Newton had already developed his method of fluxions when Leibniz began working on the differential calculus. Yet there was seemingly no proof beyond Newton's word. He had published a calculation of a tangent with the note, "This is only a special case of a general method whereby I can calculate curves and determine maximas, minima, and centers of gravity." How this was done, he explained to a pupil a full 20 years later, when Leibniz's articles were already well read. Newton's manuscripts came to light only after his death. The infinitesimal calculus can be expressed either in the notation of fluxions or in that of differentials, or, as noted above, it was also expressed by Newton in geometrical form, as in the Principia of 1687. Newton employed fluxions as early as 1666, but did not publish an account of his notation until 1693. The earliest use of differentials in Leibniz's notebooks may be traced to 1675. He employed this notation in a 1677 letter to Newton. The differential notation also appeared in Leibniz's memoir of 1684. The claim that Leibniz invented the calculus independently of Newton rests on the fact that Leibniz published a description of his method some years before Newton printed anything on fluxions, always alluded to the discovery as being his own invention. Moreover, this statement went unchallenged for some years. Rightly enjoyed the strong presumption that he acted in good faith, demonstrated in his private papers his development of the ideas of calculus in a manner independent of the path taken by Newton. According to Leibniz's detractors, to rebut this case it is sufficient to show that he saw some of Newton's papers on the subject in or before 1675 or at least 1677, obtained the fundamental ideas of the calculus from those papers. They see the fact that Leibniz's claim went unchallenged for some years as immaterial. No attempt was made to rebut number 4, which was not known at the time, but which provides the strongest of the evidence that Leibniz came to the calculus independently from Newton. This evidence, however, is still questionable based on the discovery, in the inquest and after, that Leibniz both backdated and changed fundamentals of his original notes, not only in this intellectual conflict, but in several others. Assuming good faith, however, Leibniz's notes as presented to the inquest came first to integration, which he saw as a generalization of the summation of infinite series, whereas Newton began from derivatives. However, to view the development of calculus as entirely independent between the work of Newton and Leibniz misses the point that both had some knowledge of the methods of the other and in fact worked together on a few aspects. in particular power series, as is shown in a letter to Henry Oldenburg dated October 24, 1676. Where Newton remarks that Leibniz had developed a number of methods, one of which was new to him. Both Leibniz and Newton could see by this exchange of letters that the other was far along towards the calculus, but only Leibniz was prodded thereby into publication. That Leibniz saw some of Newton's manuscripts had always been likely. In 1849, Gerhardt, while going through Leibniz's manuscripts, found extracts from Newton's De Analyse per Equationis Numero Terminorum Infinitas in Leibniz's handwriting, the existence of which had been previously unsuspected, along with notes re-expressing the content of these extracts in Leibniz's differential notation. Hence, when these extracts were made becomes all important. It is known that a copy of Newton's manuscript had been sent to Tschirnhaus in May 1675, a time when he and Leibniz were collaborating. It is not impossible that these extracts were made then. It is also possible that they may have been made in 1676, when Leibniz discussed analysis by infinite series with Collins and Oldenburg. It is a priori probable that they would have then shown him the manuscript of Newton on that subject, a copy of which one or both of them surely possessed. On the other hand, it may be supposed that Leibniz made the extracts from the printed copy in or after 1704. Shortly before his death, Leibniz admitted in a letter to Abbé Antonio Schianelli that in 1676 Collins had shown him some of Newton's papers. But Leibniz also implied that they were of little or no value. Presumably he was referring to Newton's letters of 13 June and 24 October 1676, and to the letter of 10 December 1672, on the method of tangents, extracts from which accompanied the letter of 13 June. Whether Leibniz made use of the manuscript from which he had copied extracts, or whether he had previously invented the calculus, are questions on which no direct evidence is available at present. It is, however, worth noting that the unpublished Portsmouth papers show that when Newton went carefully into the whole dispute in 1711, he picked out this manuscript as the one which had probably somehow fallen into Leibniz's hands. At that time there was no direct evidence that Leibniz had seen this manuscript before it was printed in 1704, hence Newton's conjecture was not published. But Gerhardt's discovery of a copy made by Leibniz tends to confirm its accuracy. Those who question Leibniz's good faith allege that to a man of his ability, the manuscript, especially if supplemented by the letter of 10 December 1672, sufficed to give him a clue to the methods of the calculus. Since Newton's work at issue did employ the fluxional notation, anyone building on that work would have to invent a notation, but some deny this development. The quarrel was a retrospective affair. In 1696, already some years later than the events that became the subject of the quarrel, the position still looked potentially peaceful. Newton and Leibniz had each made limited acknowledgments of the other's work, and L'Hôpital's 1696 book about the calculus from a Leibnizian point of view had also acknowledged Newton's published work of the 1680s is nearly all about this calculus, while expressing preference for the convenience of Leibniz's notation. At first, there was no reason to suspect Leibniz's good faith. In 1699, Nicolas Féchet de Douillet had accused Leibniz of plagiarizing Newton. It was not until the 1704 publication of an anonymous review of Newton's tract on quadrature, a review implying that Newton had borrowed the idea of the fluxional calculus from Leibniz, that any responsible mathematician doubted that Leibniz had invented the calculus independently of Newton. With respect to the review of Newton's quadrature work, all admit that there was no justification or authority for the statements made therein, which were rightly attributed to Leibniz. But the subsequent discussion led to a critical examination of the whole question, and doubts emerged. had Leibniz derived the fundamental idea of the calculus from Newton. The case against Leibniz, as it appeared to Newton's friends, was summed up in the Commercium Epistolicum of 1712, which referenced all allegations. That document was thoroughly machined by Newton. No such summary of the case for Leibniz was issued by his friends, but Johann Bernoulli attempted to indirectly weaken the evidence by attacking the personal character of Newton in a letter dated the 7th of June 1713. When pressed for an explanation, Bernoulli most solemnly denied having written the letter. In accepting the denial, Newton added in a private letter to Bernoulli the following remarks. Newton's claimed reasons for why he took part in the controversy. I have never, he said, grasped at fame among foreign nations, but I am very desirous to preserve my character for honesty, which the author of that epistle, as if by the authority of a great judge, had endeavored to wrest from me. Now that I am old, I have little pleasure in mathematical studies, and I have never tried to propagate my opinions over the world, but I have rather taken care not to involve myself in disputes on account of them. Leibniz explained his silence as follows. In a letter to Conti dated the 9th of April 1716, in order to respond point by point to all the work published against me, I would have to go into much minutiae that occurred 30, 40 years ago, of which I remember little. I would have to search my old letters, of which many are lost. Moreover, in most cases I did not keep a copy, and when I did, the copy is buried in a great heap of papers, which I could sort through only with time and patience. I have enjoyed little leisure, being so weighted down of late with occupations of a totally different nature. While Leibniz's death put a temporary stop to the controversy, the debate persisted for many years. To Newton's staunch supporters this was a case of Leibniz's word against a number of contrary, suspicious details. His unacknowledged possession of a copy of part of one of Newton's manuscripts may be explicable, but it appears that on more than one occasion, Leibniz deliberately altered or added to important documents, before publishing them, and falsified a date on a manuscript. All this casts doubt on his testimony. Several points should be noted. Considering Leibniz's intellectual prowess, as demonstrated by his other accomplishments, he had more than the requisite ability to invent the calculus. What he is alleged to have received was a number of suggestions rather than an account of the calculus. It is possible that since he did not publish his results of 1677 until 1684, and since the differential notation was his invention, Leibniz may have minimized, 30 years later, any benefit he may have enjoyed from reading Newton's work in manuscript. Moreover, he may have seen the question of who originated the calculus as immaterial when set against the expressive power of his notation. In any event, a bias favoring Newton tainted the whole affair from the outset. The Royal Society set up a committee to pronounce on the priority dispute, in response to a letter it had received from Leibniz. That committee never asked Leibniz to give his version of the events. The report of the committee, finding in favor of Newton, was written by Newton himself and published as Commercium Epistolicum early in 1713. But Leibniz did not see it until the autumn of 1714. The prevailing opinion in the 18th century was against Leibniz. Today the consensus is that Leibniz and Newton independently invented and described the calculus in Europe in the 17th century. It was certainly Isaac Newton who first devised a new infinitesimal calculus and elaborated it into a widely extensible algorithm, whose potentialities he fully understood. Of equal certainty, the differential and integral calculus, the fount of great developments flowing continuously from 1684 to the present day, was created independently by Gottfried Leibniz. One author has identified the dispute as being about profoundly different methods. Despite points of resemblance, the methods of Newton and Leibniz are profoundly different, so making the priority row a nonsense. On the other hand, other authors have emphasized the equivalences and mutual translatability of the methods. Here Guicciardini appears to confirm L'Hopital. The Newtonian and Leibnizian schools shared a common mathematical method. They adopted two algorithms, the analytical method of fluxions, and the differential and integral calculus, which were translatable one into the other.